Video we're going to focus on the zero product property and how it relates to quadratic functions specifically and the graphs. So let's go ahead and start by taking a look at this top left corner up here. It says recall that we refer to this form of a quadratic equation as intercept form. Okay, so intercept form is any quadratic function of the form y equals some a value. Of course, we appreciate the a value times these two quantities or these two factors. That's what I want to call it. These are factors. Okay, and so essentially these two factors here are x minus p and x minus q. We say the x-intercepts are located at p comma 0 and q comma 0. So basically what we're saying is, I mean, if you had a parabola in general, you know, is what we call these u-like graphs, and we had a couple of intercepts here, we could say that this is some p comma 0 and this would be some q comma 0, but basically they would have to correspond to these two numbers that are given here. And the one thing I want to make sure that everybody's clear on is this, that p and q here are opposite of what they would be represented as down here. That is, if we had some function like y equals 2 times x minus 1, x plus 2, we could say that automatically I know that its intercepts are at positive 1 comma 0 and negative 2 comma 0 just by looking at these and saying, well, it looks like the opposites of those. So what we're going to do is we're going to summarize a very, very profound property with real numbers that's going to help us kind of describe why we get these two things as intercepts in the first place. And then we're going to give these two x-intercepts a couple different names. So the zero product property, what does it say? It's a pretty cool thing, actually. It says given several factors. Okay, recall that factors are things that we multiply together, like these two things over here, to get something. So we say given several factors, if they have a product of 0, so if they multiply to be 0. That's what I want to say there. So if they have a product of 0, then at least one of the factors must be equal to 0. So basically, you know, in a nutshell, we basically represent this often very elegantly this way. If two things, a times b equals 0, then either a was 0 or b was 0, or both were 0. But basically, what it's saying is, in general, and this could be c extended to a times b times c equals 0, even. But basically, if a bunch of stuff multiplies out to be 0, you know, somebody was 0. So this thing, what it allows us to do is search for x-intercepts in the traditional way, which is when you look at the graph of an equation, we say, how do you find where it hits the x-axis? And what I can do is I can promise you this, put a random point out here on the x-axis. This may have some x value, but I guarantee you it has a y value of 0. So to find x-intercepts, what we typically do is you set the y value equal to 0. And then you, solve for x. So in the event that we have something like this, and I'll keep it really elegant, x minus p times x minus q, this is kind of like saying this is some a times some b. And if we can write it this way, we say, well, if I wanted to find where my graph hits the x-axis, what we could do is this. We could just simply plug in 0 for y, which that means I have to put in a 0 right here, and solve for x. See, in this event, though, the nice thing about this is, since two things multiplied out to be 0, then either, we could say this, we can come to this conclusion, either a is 0 or b is 0, or they were both 0. So what this means is we can take each of these individual expressions now and set them individually equal to 0. So x minus p is equal to 0 and x minus q is equal to 0. And you can see how we arrive at the conclusion if we're going to solve for x in each of these equations. We would add, say, p to both sides over here and arrive at the conclusion that x is always equal to p in this event. And then we say adding q to both sides here. 0 plus q, of course, is q. So we get x equals q. So we say when y equals 0, that is what we say up here, when y equals 0 here and here, or when y equals 0 here. I actually have to put two y values because we got two different x values. We say p and q, and these were the 2 points on our graph. So now that we're familiar with the zero product property that basically says, hey, when you multiply a bunch of stuff together, you can actually set each individual factor equal to 0 and then solve for in individual parts, okay, instead of having to solve the whole thing at once. So what we're going to do here is this. In example 1, it says use the ZPP, or the zero product property, to find the x-intercepts for the graph of the quadratic equation. Then what we're going to do is we're going to sketch it and say some things about it. So let's start with the x-intercepts. We say to find the x-intercepts, recall that what we need to do is this. To find x-intercepts, let's table this out. We need to plug in 0 for y. And I'm going to be putting in another 0. We're going to see y here in a second. But I already noticed this is in an intercept form. So as a matter of fact, I can just look at this and say, well, I know the intercepts have to be the opposites of these numbers here. So I know already that I'm going to get negative 1 for one of my x values and a positive 3 for my other x value. But what I want to do is actually use the zero product property this time, which means I have to show some work down here. And what we're going to do is this. We're going to plug in 0 for y. So I get 0 equals 2 times x plus 1, x minus 3. Now the first thing I want to point out here is this 2 in front. What I'm going to do is I'm going to divide both sides by 2. And you know what? It's not going to matter as a matter of fact because 0 divided by anything is 0. We're just going to get this x plus 1, x minus 3. So the first thing I want to point out is you can see how these are the only things I care about here, the factors. And now since we have something times something equals 0, we can set each individual factor equal to 0 and solve this. So I get x minus 3 equals 0. And I get x plus 1 equals 0. And solving these, subtract 1, we get x equals negative 1 for this x-intercept. And we say adding 3 to both sides here. We say we get positive 3 for this x-intercept. So these are the same ones that we got up top. I will say this, hey, if it's intercept form, I would just encourage you right now to just recognize them from these two factors, okay? But that is how we arrive at it from the zero product property. Of course, this makes sense. So now we say the x-intercepts, let's go ahead and put them here. We say we have negative 1, 0, and comma, 3, comma, 0. I should have put this in a different color, but I'm going to go ahead and put those on my graph. So we say negative 1, 0 is here. And then we say, okay, so 3 zeros out here. So we know because of symmetry, if these 2 points on the graph, then right down, kind of the middle of these two things has to be this imaginary vertical line that we call the axis of symmetry. So this axis of symmetry, which is, by the way, the average of these two x values, we say the average of negative 1 and positive 3, we can actually find this. Is 2 over 2, which is equal to 1. So what we say is x equals 1. We want to label this equation here. So we say the axis of symmetry is x equals 1. And then furthermore, we say, well, the vertex also has to have an x value of 1. How do I find the y value? We need to go find f of negative 1, which means we're going to go plug this x value into the original equation. Now, I want you to keep in mind the original equation, which is this one right here. We say minus 3 plus 1, we had those. We're actually plugging into these points right here. So this is very important. You put in blank parentheses. We say a negative 1 there and there. You have to forgive my mess here. We say y actually equals 2 times negative 1 plus a positive 1. Okay, so we'd say, all right, negative 1 plus x, let's see, are we plugging in a negative 1 here? Oh, that's why. I'm sorry. This is totally a positive 1. Okay, sorry. Positive 1. I don't know why I put a negative 1 here. Forgive me. This is going to be 1 plus 1. Forgive. 2, let's see. 1 minus 3 is negative 2. And so we get a product of negative 8. All right, so this is much better. So we say at an x value of negative 1. We are at a y value of negative 8. And by the way, this is a positive 1. Again, I did it again. So we say 1 comma 8. Negative 8, we say 1, 2, 3, 4, 5, 6, 7, 8. So this is our vertex. We always want to label the vertex if we can help it. So let's go ahead and do that. And we say then we have this parabola that I'm trying to get to look nice here that goes up through these 2 points right here. And there we go. And we should label this. We should call this what it is. We say y equals 2x plus 1 x minus 3. So a few things before we sign up on this video here I want to kind of point out, or at least question. It says, what were the key points on the graph of the equation? Well, the key points here are these two x-intercepts. We say the x-intercepts are definitely key points. I would write that right there. And then also this, we say the vertex. The vertex, of course, the vertex and the x-intercepts. So those being said, I have one question here. It says, how did the values of the x-intercepts relate to the values of the factors that we started with? And when I talk about factors, again, up here, this whole right side is factored. It's something times something times something. I said, how do these factors, how do they relate to the actual x-intercepts? And I'm saying, question this right here. And I noticed that the x-intercepts were always just backwards of kind of what the factors look like, and that just goes back to what we have up here in the top left corner. So that's how we use the zero product property. That's what it is, and that's how it comes in handy in finding x-intercepts. Cheers.